Uh-huh. Uh-oh. Okay. All right. Okay. Um, go. All right. So we got a slight change of plans. It's a pretty big change of plans. All right. So we are not going to do waves. We're not going to go over waves. We're gonna drop that because I really want to go at least over thermal energy, heat, and temperature. I want to go over that. So I need to go ahead and update our schedule, lecture schedule that we have set up. But let's see. Let me show it here. Okay. So this is where we're at, right? So we're already behind by a day according to this, because we had to go ahead and take 6 days for the circular motion instead of just 5. It takes 6 days to get through it all. So we're gonna forget waves, right? That's number one. We're not gonna do waves. We're gonna skip that. Second thing is I can't have class on Friday, so I won't have class on Friday. I'm not gonna show video, nothing. We're just gonna say we're just gonna nix it. So no class Friday. Apologize for that. I know I've had to do that a couple times. It's one of the downfalls of me being here. So no class on Friday. On Monday, we'll go ahead and we'll do a review. Okay, so usually I don't do reviews, but we'll do a review. And we'll have an exam 3, okay, on this Wednesday. All right, so exam 3 on Wednesday. We'll review for exam 3 on Monday next week. And exam 3 will only cover circular motion and harmonic motion. And I think that that's okay because circular motion covers a lot of stuff. Okay, so the bulk of the test will come from circular motion, and we'll just get like a couple questions from harmonic motion, and that'll be it. And we'll talk more about what that looks like on Monday, okay? And then we'll do thermal energy. We'll review for the final exam, and the final exam is comprehensive. It will cover everything we've seen. I'm thinking of going from, well, we'll discuss it when the time comes. I don't want to get too far ahead of myself. Okay, so again, we're not doing waves. Waves is out. No class Friday. We're not going to meet. Monday review for exam 3. Wednesday I'll probably open up exam 3 for Tuesday and Wednesday, so you have options for that. And then we'll do thermal energy, heat, and temperature. Okay. Any questions?
No, sir.
Okay, so last time, no waves, no class Friday, review on Monday, exam 3 on Wednesday, and then we'll continue with the schedule as we see it here from that point. We're almost done. We're almost done. We've got the bulk of the most important stuff. Why isn't this joining? The most important stuff is done. Waves is, it's not that it's not important because energy is transferred through waves. Very important concept, but I just won't have time to cover it. If I have to choose between waves and the thermal energy, I'd rather do the thermal energy, heat and temperature, because you need at least to have some kind of basic knowledge of that stuff. So there we go. Why isn't it minimum? Okay, so let's get to the notes. Let's get to finishing. We'll finish harmonic motion today. Okay, so the period of a mass spring system. All right, so again, mass spring. We've got this mass on a spring. There it goes. Okay, and we're going to start with Newton's second law again. F equals ma. And we know that F is negative kx. It acts in the opposite direction that's being pulled. So that's the force on the spring. So solving this for A, we're going to get a negative k times x divided by m. All right. But we know that A is also a negative omega squared times x. So we're going to make these things equal to each other. So negative kx over m equals to negative omega squared x. So this x goes, this x goes. And we're going to solve this for omega. So omega squared becomes k over m. Right? The negatives cancel. The x's cancel. So we end up with an omega squared equals to k over m. So we'll leave it there. So there's one equation relating the spring constant to omega. So the spring constant and the mass will determine what omega is going to be. Okay, so we can say omega is equal to the square root of k over m. So that's an important equation. Don't dismiss that one. But we're talking about the period here. So we know that the period is equal to 2 pi over omega. Okay, and that just comes to, we said before that omega is equal to 2 pi over t. So t is equal to 2 pi over omega. Actually, I want to solve for omega. So let's just do this. We know omega is equal to 2 pi over t. This is squared. I'm going to go ahead and square everything here. So we're going to end up with an omega squared equal to 4 pi squared over t squared. Okay, so this equals to this. So we have k over m equal to 4 pi squared over t squared. We can solve this for t. Multiply both sides by t squared. So we end up with a t squared times k over m equal to 4 pi squared. Multiply both sides by m over k. That goes, that goes. We end up with a t squared equal to 4 pi squared times m over k. Square root both sides. T equals to 2 pi times the square root of m over k. And so you'll see that we can find the period based off just the mass, right? So we have the period in terms of mass and spring constant, right? So that's one thing. The next thing we need to notice here is that T is not dependent on amplitude. So it doesn't matter how far I pull that spring, the period's going to be the same. Okay. Which is interesting, right? That's kind of hard to understand when you think about it, but it doesn't matter how far I pull out that the mass away from equilibrium, the period's going to be the same. That's interesting. Okay. Last thing we have to talk for a mass spring system is energy. And remember that total energy is equal to the kinetic energy plus the potential energy. All right, for a mass spring system, that means that we're dealing with kinetic energy, we're dealing with 1/2 mv squared. Right, that's the kinetic energy. And we're dealing with the potential energy of a spring, which is 1/2 kx squared. All right. We know that x is equal to a cosine omega times t plus phi. And we also know that b is equal to negative omega a sine omega t plus phi. Right, so here comes the crazy part. I have to put both of those into these equations here, so it's a lot of work. So E is equal to 1/2 mv squared, so I have to take all of this and put it here, so it's negative omega a sine of omega t minus phi, all that squared, plus 1/2 k times x squared. X is all this, so a cosine omega t plus phi squared. Right? So we got to square all this stuff. This is going to give me a positive omega squared a squared sine squared omega t plus phi. And on the other side, in the other term, we're going to have 1/2 k times a squared cosine squared omega t plus phi. Right, so now I'm just going to bring everything out. So we have 1/2. Let's do it just so that you guys can see this a little bit more clearly. Yeah, 1/2 m omega squared a squared sine squared omega t plus v plus 1/2 k a squared cosine squared omega t plus v. All right. We know that omega squared is equal to k over m. We just saw that, right? So I'm going to replace this here. And so I'm going to end up with E is equal to 1/2. The mass is going to cancel out. So I get k a squared sine squared omega t plus v plus 1/2 k a squared cosine squared omega t plus v. All right, so you'll notice that this term and this term are the same. So we have a sine squared something plus a cosine squared something. Right, and so there's a trig identity that says that sine squared theta plus cosine squared theta equals to 1. All right, so if we replace the theta with the omega t plus v, which both of these have, then everything in this block here is going to go to 1. So all of this here goes to 1. So we end up with E equal to 1/2 Ka squared. That's the energy of a mass spring system. All right, so if I know the spring constant and I know the amplitude, then I know how much energy is in the system. Also note that the energy is dependent here on A. It is dependent on the amplitude. Right, and so that's it for a mass spring system for simple harmonic motion. Next, we're going to do an example, and then we'll look at the pendulum. But just to put everything together, simple harmonic motion constants for mass spring system. We have the amplitude A, so that's one constant. We have the period for a spring, right? So this is only for a spring. You have to do something a little bit different for the pendulum. We have frequency, which is common to both. And we have period. We have omega, which is also constant. It's for both. Omega is equal to 2 pi f or 2 pi over t. We have the phase. Okay, the phase is equal to the inverse tangent of negative v naught, so the initial velocity divided by omega x naught, so or the velocity at time equal to 0. Yeah. We have the max velocity Vm equal to omega times a. We have the max acceleration. It's omega squared times a. And we have the energy. Okay, so all of those are constant. For a mass spring system. X is not constant, V is not constant, A is not constant. V max and A max are constant because it will always go back to the same max acceleration. But as the mass changes its position, its velocity at those specific positions are going to depend on the time. Okay, so omega t plus V. So that t is what changes the X, V, and A. All right, so let's do a problem. An oscillating block. Let me give you guys a minute to give you guys 2 minutes to write this down. That was weird. Okay, an oscillating block spring system has a total energy, let's write that down, has a total energy of 1 joule. It has an amplitude of 10 centimeters, so that's 0.1 meter, and a max speed of 1.20 meters per second. So Vm is equal to 1.20 meters per second. We want to find the spring constant, we want to find the mass of the block, and we want to find the period of oscillation. All right, so A. So I need to look at all those equations and see which one I can use to find K. So I need to find some equation that has K in it. So this guy has K in it, TS has K in it, but I don't know the period. Yeah, I don't know the period. I could find the period, but I don't know the period right now. Because to find the period, I'm going to have to find omega first, and I'm not given that. So it'll be a much longer process. So going through here, I do have this equation here. I do have this equation that I can go off of. Okay, that one gives me, I know energy. Okay, I know the amplitude, so I can solve this for K and figure out what K is. So solving this for K, we're going to multiply both sides by 2 and divide by a squared. So K is going to equal to 2e over a squared. And now all I have to do is substitute in those values. It's going to be 1 joule, 2 times 1 joule over 0.1 squared. And then just plug that into a calculator. You should get 100 newtons per meter for K. The mass of the block, well, let's look at these equations and see what we got. All right, so this one has mass in it. Let's see what else we got mass in. We got this has mass in it. Okay. So again, here I don't know the period and I don't know the mass. The period is going to be, again, quite a long process to figure out because I need to figure out omega. I could do that, but it would add an extra step. So I could do this. I could find T here. and then I have to find omega first. So I'd have to find omega, then t, then plug it in up here. All right, so there's several steps there. Or I could use this equation, omega squared equals to k over m, and solve this directly for m. I know k, and so I just have to find omega. So instead of finding the period and omega, I just need to find omega. So let's go with this equation there. I hope that makes sense. The logic makes sense. So we're going to use omega squared equals to k over m. Right. So just again, you could use the other equation. It would just take a little bit longer because you have to find the period, and to find the period, you have to find omega. So it'd be an extra, some extra steps there. Here, I just need omega. I'm given an equation. I'm given the max velocity, and the max velocity, if you remember, is omega times a. I know a. I know the max velocity, so I can solve this for omega. The max velocity was 1.2 meters per second divided by the amplitude, which was 0.1. So that gives me 12 radians per second. And now I can plug that back in up here after solving for m. So m is going to equal to k over omega squared. The amplitude was 200. Omega squared, that's going to be 12 squared. And so my mass is 1.39 kilograms. Finally, we're looking for the period of oscillation. So now I've got everything I need here. We go back to find the period. I have m, I have k, so I can just use this equation here now and be done with it. So Ts is equal to 2 pi times k over m, right? K over m or m over k? M over k. Hold on. Make sure I have this written down right. M over k. Okay, and I just need to plug in those values. So that's going to be 2 pi times the square root of the mass, which was 1.39, divided by our k value, which was 200. And plugging that into a calculator, you should get 0.524 seconds. Okay. So it's just looking for the variables you're looking for and seeing which steps, which best equations to use to get to where you want to be. This is very straightforward. It's pretty much plug and play. All right, just plug and stick it into your calculator. You come out with the value. So hopefully, my hope is that it's not too complicated for you guys. Give you guys a break from the semester. It's been a long semester. All right, so the pendulum is interesting. All right, so what's going on here? We've got a mass on a cable, and it's going to go back and forth, right? So let's just say, for the sake of this example, that our pendulum is swinging up this way at this point. So this is our direction right now. Okay. As soon as the mass passes equilibrium, so as soon as the mass comes in this way, the acceleration goes in the opposite direction. Okay, so we've got an angular acceleration going this way. Okay. We're going to define so we've got what we call the tangential direction and the normal direction going in towards the center, towards where the rope is connected, right? That's going to be our That's going to be our coordinate frame. Okay, and I'm just going to extend this line. Right, and the reason I care about that coordinate frame is because I need to figure out how the weight of the object is affecting my motion. All right, so this is mg. Right, so I can break this into, make a line. If I make a line, let's go with a different color. I'm going to make a line that's perpendicular here. Okay, so that's perpendicular, and that means I've got an angle here of theta. So I want to know what this part of my weight is doing. Okay, because that's where the motion's going. Okay, so I want to know what this component of my weight is doing. Okay, that component. So I've got to figure out what it is. And in this case, this is opposite side here. Right, so this is going to be here as well. So these are going to be equivalent. This is going to be opposite is sine. So this is going to be mg sine of theta. Okay, so that's the force acting in the t direction. Right? And that's what I care about right now. I care about what's going on in the t direction. So the sum of the forces in the t direction is equal to m times a t. I know at is equal to r times alpha. All right. So I'm going to plug that in for at, and then my only force acting here is that component due to gravity, that mg sine theta. So it's going in the negative direction. This is the positive direction here. So mg sine theta is going in the negative direction. So it's going to be negative mg sine of theta is equal to mr alpha. But I know r here is going to equal to the length of this rope. So from here to here, that's L. So this is going to equal to negative mg sine of theta equal to, actually, we can also get rid of these. Let's go ahead and do that. So we got a negative g sine theta equal to m alpha, or L alpha, sorry. L alpha. Okay, solve that for alpha. And we're going to get that alpha is equal to negative g sine of theta divided by L. So note again, alpha is not constant. Okay. Also note how it looks very similar to a equals to negative k over x, negative k over m times x. All right, so if I were to write this, I could write this also as negative g over L times sine of theta. And we had a is equal to negative k over m times x. So we've got some dimensional thing going on here. In this case, it was length. Over here, it was mass. We've got a constant here. In this case, it's for a pendulum, it's the acceleration due to gravity. Over here, it was the spring constant. And then we have something dependent on position in both cases. So sine theta is position, x is position. Okay. So lots of similarities, but they're different, right? So this equation here only applies for a pendulum, right? So I can find the angular acceleration for a pendulum. And I can simplify this further by using what we call the small angle approximation. The small angle approximation says that for small angles, sine theta is about equal to theta. And so alpha then becomes negative G over L times theta. And that looks even more like this equation now, right? So I'm not going to go through the whole thing for our period, but for the period of a pendulum, it's going to look very similar again to what we saw for a mass spring system. Our equations just change a little bit. So for the spring, it was 2 pi m over k. Yeah. For a pendulum, it's 2 pi L over G. So again, they look very similar. We have the 2 pi, we have the square root, and then we have the dimensional thing. We have L and M over here. And then on the bottom, we have a constant, K for the spring, G for the pendulum. For the pendulum, X, instead of doing things in terms of X, we do things in terms of theta. Theta defines our position. So our equation becomes theta equal to theta naught times cosine omega t plus phi. All right, so very similar. I mean, the only difference there is the amplitude is now theta naught and X is theta. Okay, so that's an important equation. Again, getting to these formulas is the same as what we did with the mass spring. So I'm not going to go through all that. At t equal to 0, phi is going to equal to 0. So we're also going to come up with some constants that x naught is equal to a. That was for the mass spring, right? Here, or whenever we do that, theta is just going to equal to theta naught, obviously, right? The starting angle is going to be the starting angle. So this is an important equation. And finally, if we need to find the amplitude, if we want to find the amplitude, if we're graphing this, then A is going to equal to L times theta naught. Just like X equal to L times theta naught, or we have from the geometry, X naught is equal to L theta naught, A is equal to L theta naught. Again, I'm not going to go into all of that. It's unnecessary at this point. So this one's is that final theta, initial theta. This theta is the naught. So that naught means initial. That always the naught means at time equal to 0. That's always been the case since the semester started. So which other equation? Which other equation are you talking about? This one? This one? If you're talking about this equation, it's the same concept as we saw with the mass spring system. We're going to find some theta based off of the time. So theta changes with respect to time, and it's dependent on the initial theta. Okay, so this is theta at some time t. This is just saying that at time equal to 0 and phi equal to 0, theta whatever theta we're looking for is going to be theta naught. Theta is equal to theta naught. That's all that's saying. So obviously at time 0, the initial theta is the initial theta. Like that's all that's saying. We're usually given that theta naught, by the way. All right. Does that answer your question? Okay, good. Right. Last example. Harmonic motion is pretty simple, guys. Pretty simple. Not a lot to go on here. Yeah, we should be able to finish. Okay, so I'll give you a minute to write this down. Okay, a pendulum consists of a 60-gram mass. So I'm going to go ahead and write that down. Let's see, 60 grams is 0.06 kilograms. I think, yeah. So a pendulum consists of a 60-gram mass attached to a cord of negligible mass. Negligible mass means that I don't have to think about the mass of the cord, right? I don't care about it. It's so small compared to this mass that I don't have to consider it in my math, okay? The angle between the cord right? The angle between the cord, so this angle here, is defined as the chord in the vertical. Yeah, the chord in the vertical is defined as theta equal to 0.80 cosine of 4.43 t plus phi. All right. Okay, so I know what are the pendulum's length and period. So I know that theta naught is equal to 0.80 radians. Okay, that's something that I think I failed to mention is that whenever you're doing these calculations, make sure that your calculator is set to radians, not to degrees for these problems. Okay, for these problems, we're dealing with radians, not degrees. So be sure to set that your calculator properly. And we also know that omega is equal to 4.43 radians per second. All right. Cool. We want to know first the length. All right. Make sure I'm not getting questions. Let's see the length. Length and then the period. So to find the period, or to find the length L, the only thing, let's see, let's look at our equations real quick. The only thing that I can use, I could use this. This has an L in it. Or I could use this. And I need L and theta naught. I'd have theta naught, but I need L to find A. So this one's not going to work. I can't use that one. So let's go with TP with our period equation there. It's 2 pi L over G. Right? So I know G, I don't know L, I don't know TP. So I'm going to go ahead and do part B first. Let's solve for our period TP. So I have that equation for T, but I also have that the period, this is in general for both mass spring system and the pendulum, that the period is equal to 2 pi over omega. I know omega. It's given to me in that equation. So T is equal to 2 pi over, what was omega? 4.43. Plugging that in, you should get 1.418 seconds. Okay, so now I can solve this one over here for L. I'm going to square both sides. So TP squared equals to 4 pi squared times L over G. Let's multiply both sides by G. So I end up with a TP squared times G equal to 4 pi squared over L. 4 pi squared times L. Divide both sides by 4 pi squared. And I get that L is equal to the period times the acceleration due to gravity divided by 4 pi squared. So now I just need to insert or substitute in those values. That's 1.418 squared times 9.81 divided by 4 pi squared. Plug that into your calculator, and you should get that the length is about 0.50 meters. Let me check that one to make sure that's correct. Because squared. Oops. Yeah. No. What did I do? Oh, I forgot to do this. Put all of this in. There we go. This is 4. There we go. Yeah, 0.5. 0.5 meters. That's right. Okay. And this was my period. Done. All right. Any questions?
I just need to copy it down for a second.
Okay. Zoom out on that a little bit. This will show.
Are you gonna give us another homework, sir, before the exam?
There's already a homework. It should have popped up. You guys didn't see it? Did it not pop up? Did I forget to publish?
Oh, I didn't.
Yeah, it's there. Harmonic motion homework. It's due tomorrow, actually. Okay. I'm going to change the date on that. Let's make it due Friday.
Okay.
There we go. Yeah, it's due Friday, midnight, before 11:59.
Sounds good, sir.
Alrighty.
Okay, thank you.
All right. We'll see y'all. Again, no class Friday, so I'll see you guys. If you have any questions, of course, I'll have my email there with me. I have my phone with me, but we won't be meeting. We'll see you guys on Monday to review.
See you soon.
Take care, sir.
All right. Bye, everybody.